some aspects of quality software development and what are the practices that we should use when measuring our software and developing towards quality. So, first question that we have to address is why do we need to measure? Why measurement? So, we can see that if you want to compare two different things, you need to measure. You can say that a person is taller than the other or a person is heavier than the other. When you can measure, you can compare, and when you can compare, you also have a choice. That means you have some sense of quality, and that quality is quantified in terms of the values after measurement, and once you measure, you can decide. So, choice is possible and then progress is possible. So, if you know that something is wrong or something is not as per the quality, for example, your code may not be efficient, you have measured the efficiency, now you can strive to achieve higher efficiency or say utilization. So, once you are able to measure, you have some quantities with you, that is numbers. Now, you know what is expected, and in order to improve, you can also objectively try to achieve better measures or higher quality. So, measurement helps us distinguish different things. That means, we are able to compare, and we are able to capture quality in terms of some quantity, or we are trying to quantify the qualities, and once we are able to do that, we will be able to exercise our choice, and also we will be able to progress, or we will be able to make corrective steps. We can encourage quality once we have the numbers based on, of course, the numbers. So, basically when we want to deal with software, we want to have these objective measures, so that different people can use it. Once you have an objective measure, everybody understands the meaning, and there is only one way to calculate these numbers, then there is uniformity in practice. So, we want to have these objective measures, and then we want to apply these measures to various tasks. So, if we are able to measure our software, we can compare, we can exercise choice, and we can also improve based on the measure. So, these are the important considerations which drive this the practice of measurement in software engineering. So, what is the use of software measurement? This slide captures some of the points. How good is the design? So, if we measure, we will be able to know whether our design is good or bad. So, bad designs are mostly hard to understand, implement, maintain and evolve. So, your software might be correct, but the design of the software may be very complex. So, once I had tried one experiment for a small problem in a class. In my class, there were about 20 to 25 designs. So, now if we have many designs for the same problem, you have to choose one of them. So, you should be able to measure, you should be able to tell objectively which design is good and bad. So, that we should strive to achieve. So, we should find out if there are any objective criteria with which we can measure our designs. So, we can, for example, we can say I am using 10 classes to achieve the solution, somebody else might be using 3 classes, somebody else might be using 5 classes. So, which one is better? So, you cannot say if I use less number of classes or lesser number of classes, I have a better design, or I use too many classes, I have a better design. So, there must be some criteria to firstly to measure, that means to count and to come up with the measures, and then to compare them, to associate them with quality factors in software engineering. So, one important point is about design. Then we also need to look at the code. Complex code is mostly hard to understand, test, debug and change. So, if the code is very complex, it will be hard to understand. So, sometimes it also deals with styles. So, the algorithm could be same, but the code that is written by different people also it differs. How much efforts will be required? This is another use of software measurement. So, if we have the measures of your software, or if you can predict, for example, the number of classes that are going to be required to implement your software, you can find out how many people will be required, how much time is required. That means you can estimate your man months, you can estimate your costs. So, to develop the software, you need to find out how much efforts are going to be required, and this deals with your management aspect of software. So, in order to design, implement, test, maintain, debug and deploy, how much efforts will be required. So, these measures can also be useful from that point of view. So, that is to say that software measures help in decision making in various life cycle phases. So, this is the underlying motivation, that if you are able to measure your software product and also the process, it basically helps you in various kinds of decision making in various phases of your software life cycle. So, what are the attributes that can be captured? That means, what you can capture through these measures about software. So, basically we are trying to capture software quality, how good is the product, efforts or resource estimates, we can capture them, progress of development, how far you have progressed, how much is still remaining. So, that is the most important question which everyone wants to ask when you are developing in front of with deadlines in front of you. And complexity or difficulty, how complex is the task, how difficult is the task, you obviously want to measure this, or you want to capture these attributes through your measures. Process quality also, how good is your software development process, you want to capture if possible. So, quality factors, usability, correctness, efficiency, modularity, portability, simplicity, understandability, security, robustness, completion, that means how much you have completed, how many functions, how many use cases have been over. So, is it 90% complete, 95% complete. So, you want to have these measures, and based on these you have some assessment of the quality of your software. So, measurement is quite important, and these are the attributes which we would like to capture: quality of your software, of your process, the progress of your development, then the complexity and difficulty, and also the efforts or your resource estimates. So, we would like to capture these through measures and correlate these numbers with some of these, with these quality attributes. So, in this lecture we are going to look at some of the basics of measurement and see and look at the motivation and various measures and some important properties associated with measurement, so that we have a good introduction to measurement. And then we will also look at how you can organize your process and how you can use some of the good practices which are known in the software community, or which are well established as good practices. So, first we will take a look at different aspects of measurement. So, which one is a good measure? That is a question which comes to our mind. So, lines of code, is it a very good measure? Will it capture everything that we just said? So, consider, for example, you have a 1000 line program and a 500 line program. So, can you say that 1000 line program is more complex than the 500 line program? So, how can you use this measure? So, this is a measure, LOC, lines of code. So, this definitely tells you about the code size in terms of number of lines, but does it reflect on how good the code is, how complex the code is? Is it a high quality code? Can you say that 1000 line program is a high quality code and 500 line program is a low quality code, or can you say that 1000 line program is more complex than 500 line program? So, you cannot make these statements, but you can say that 1000 line program is larger than 500 line program in terms of number of lines, that much you can say. So, LOC is a measure, it tells you about the length of the code. Maybe you can associate this with time required to understand the code. Say if I have 1,000,000 lines of code, I can have some estimates from that number. If I know that I have a 100-line program, I can have some estimates about the efforts required, the time required to understand and so on. So, it is useful, but it cannot capture everything. So, that means we need to associate the appropriateness of a measure to when we are using it in a specific context. So, for example, LOC can be appropriate in one context, but not in another. So, this leads to question what to measure. So, you can of course measure lines of code and use it. So, what to measure, and the answer depends on what is your need. So, where are you going to use these measures, for what purpose. So, now there are plenty of measures available, and you can go through the metric databases, or there is a lot of material available, papers are available. So, many measures are available, and you can use appropriate measures in a given context. Now, so the important point that we want to highlight is what to measure depends on what is your purpose, and accordingly you can choose the right measure and apply it to your context. So, we will have some attributes mentioned here on this slide. What to measure in software? What can we measure? Can we measure length of the software? Can we measure the size? So, the answer is yes, but the units are different. So, you want to measure the size, you can look at the lines of code. For example, there are different kinds of size measures. So, size you can measure togetherness of modules components. So, we know that we want to achieve high cohesion within a module. We do not want to put unrelated things, unrelated functions, or completely unrelated classes in one module. So, that property is the cohesion property. So, you want to have high cohesion, that means the module should be together. So, we want to measure this togetherness of modules components, and we also want to measure dependence of modules on each other. That means how much a module depends on another module. So, we want to achieve a very good separation of our components or modules, so that they are independent. Once we have this good modularization, we know that we can do parallel development, we can give different modules to different programmers, we can test them differently, and then only we have to make a build. So, independence or separation of concerns is a very important principle in software engineering. So, you want to separate these concerns and you want to reflect them into different modules which are separated. So, we also want to measure this separation, how separated they are they really coupled. So, coupled together, or are they very highly coupled. So, there has to be some coupling because modules interact. So, you do not simply have your software as simply completely independent modules, otherwise it will be simply a collection of library. You want the software that is executing and that has lots of collaborating components. So, coupling will be there, but how heavy is the coupling, how modules are interdependent on each other. Is it a very spaghetti coupling, or is it a very clean structured decomposition where you have a very good low coupling, and but there is collaboration through low coupling, and you have very highly cohesive modules. So, each module is together. So, the components in a module are together, but different modules are not very tightly coupled to each other. So, this is what you would like to achieve. So, you want to achieve high cohesion, low coupling, and at the same time you want to achieve separation of concerns and also collaboration. So, if we have these measures of coupling and cohesion with us, we will be able to tell whether a given module is highly cohesive or it is low on cohesion, and then reflect back on the programmer and ask the programmer to, or the designer to improve on the design or the code, whichever is the cause of this cause of bad coupling or bad cohesion. So, dependence of modules on each other we would like to measure. Then we would like to measure code complexity or organization of code. How complex is your code? How good organization have you? Whether the organization is good or how bad it is. Defects discovered per lines of code. So, we want to find out how many defects have been discovered so far. So, if you have 100 lines of code and if you have discovered 20 defects. You have 20 by 100, so you have one defect per say 5 lines of code, and if you have the same number of defects for a larger program, that means there the program is probably better or less error prone. So, this is a good measure. It does not see defects also are of different severity. So, you may have smaller number of defects, but they could be very severe, whereas trivial or minor defects, but more in number may be more tolerable than lesser defects, but severe. Say specifically say in mission critical systems, if there is one defect that shuts down the whole system, it could cost very heavily. So, defects discovered per lines of code is of course a good measure, but it does not tell you about the severity of your defects. So, that is something different. So, but however, it is a measure and it can tell you whether the programmer is making many mistakes and so on. So, during testing you have to measure this. So, not only that you are measuring your software, your source code, but you are measuring also during your testing phase. You are measuring number of defects that are being discovered for a given module or a code, and then you can relate it to people or the resources involved and try to improve. So, we can use these measures, we can feedback these measures into the process and improve on the quality of the software. So, then time spent on different processes, you can measure the times and then so that you can control the process well. The number of requirements for your software we can measure. So, if you have too many requirements, so a simple measure could be just number of use cases in your requirements document. So, if you have too many use cases, you have some measure of how much it is going to take to carry out this project. So, you would like to measure these things. So, these are some examples. So, based on the goals of your measurement and what you want to measure, you need to gather data. So, this data collection is important. So, you need to gather the related data in order to measure. So, sometimes the data can be collected automatically. You can write tools which can directly give you measures. So, for example, if you are measuring your code, you can write tools and get these measures, and during testing also you can count number of defects and so on, and few measures could be also the data could be manually maintained in form of tables and so on. So, it is important that appropriate life cycle stages you keep an accounting system and you keep gathering the data, so that you can collect these measures and then you can feed back into the quality of the software. So, that is the important point. So, that once you measure your software, once you have these measures, you can use them to choose to improve upon the software. So, to improve the quality of the software. Now, we will look at some aspects of measurement. So, what are the different kinds of there are different kinds of measures, can we classify them? So, one important concept to study in measurement is scale. So, we could have measures on different scales. They are called nominal scale, ordinal scale, interval scale, ratio scale, absolute scale. So, let us look at these scales, what they are and what kinds of measures we have and what can we do with them. So, the first one is the nominal scale. So, on the nominal scale, items are assigned to groups or categories. No number is generated. For example, you can't have ordering, no ordering is implied. So, you have no quantitative information is generated, but you have groupings or categories. Examples are whether your programs are recursive or non-recursive programs, or programs that use portable features and those that use non-portable features, binary executable programs, source programs, DLL components, object libraries. So, you can classify them or categorize your programs or functions or modules in these different classes or different types of errors. So, it is one way so it is basically classifying. So, this scale you get groupings or categories, but you can't order them. So, you can't say one is better than the other, or you can't have on this using this measure you basically say this is different from the other, and it is a qualitative difference, but there is no quantity associated with this, but we do use these measures and they are also very helpful. Then you have the ordinal scale on which you order your measurements. So, measurements are ordered, so higher number can represent a higher value, lower number represents a lower value. So, but the numbers are only for the purpose of ordering. Say for example, cold, warm, hot. This is an ordinal scale. So, but you can't say whether cold means 1/3 as hot or hot is cold plus warm. So, these numbers are basically for the purpose of ordering, or in this case cold, warm, hot. You can say cold is 1, warm is 2, hot is 3, but you cannot say hot is cold plus warm, and or you can't say cold means 1/3 as hot. For example, you have CMM maturity levels: initial, repeatable, defined, managed, optimizing. So, these gives you an ordinal scale. How often software fails? Daily, weekly, monthly, yearly, or never it fails. So, or software has never failed. So, you have this ordinal scale. So, ordinal scale is also useful and is also often used in software engineering. Then you have the interval scale, where you have intervals that separate classes, and the interval is known. So, that is based on value. You know exactly when the item crosses one class and goes into another. So, the classes are ordered, different classes or the categories are ordered. Addition and subtraction is fine, but you can't take ratio. You can't use multiplication and division. So, for example, temperature in Celsius or Fahrenheit scale, you can say that 30 degree centigrade to 31 degree centigrade or 20 to 21 degree centigrade is 1 degree hotter than earlier, but you can't say 50 degrees is twice as hot as 25 degrees. So, the example in software engineering is logs of events on different dates. You can't say yesterday was half today, but you can say that today is 1 day more than yesterday. So, you have these intervals and they are also ordered. Addition subtraction is fine, and addition subtraction is not fine in the ordinal scale, which is possible in the interval scale. So, then we have the ratio scale. Ratio scale has ordering, interval sizes, and ratios are also possible. So, value 0 is available and it represents absence of the measured attribute. Example, you have length 5 feet is half of 10 feet, temperature on Kelvin scale or LOC, length of code, as statement count. So, you can say 100 lines is half the length with respect to 200 lines. So, and then you have the absolute scale, counting entities in the entity set, where you can simply count the entities. So, all arithmetic operations are meaningful and there is only one way to measure, that is by counting. So, length of program when measured as statement count LOC is not the absolute scale, as you can measure it in different ways. For example, you can have number of lines or number of words, etc. But LOC as statement count is absolute scale measure of number of lines of code. So, if you are saying that I am simply measuring number of lines of code, then the LOC is absolute count. Number of failures, number of project engineers. So, these are your absolute scale measures. Now, let us look at some of the metrics which we can use in the software life cycle. Say for example, you have length, which gives you physical size of the product. It is not enough to understand the real complexity in order to estimate efforts, cost, etc. So, the length or number of lines of code will not, it is not enough to gauge the real complexity, but it is a useful measure. Then the functionality. So, size can be also found out in terms of functionality, how heavily how much functionality is present in the software, how loaded is the software in terms of functions or the functionality that it provides. So, these are also some size metrics, and then the complexity metrics mainly talk about or mainly provide the measures of the problem complexity, algorithmic solution complexity, structural complexity or cognitive complexity. There is an understandability of your software, how easily you can understand your software. So, these are various aspects of complexity. So, these are basically your various size metrics. So, you are trying to measure your software size in terms of these aspects. length, the length of the software or the functionality of the software. So, the size in terms of the functionality provided or the complexity of your problem domain and the solution. So, let us look at length, and it is a simple set of metrics. So, you have lines of code, but when you say that you have say 1000 lines of code, you have to also specify what have you done with comments, blank lines, data declarations, or if you had say more statements on one line of your printout, how did you count them. So, when you measure LOC, you have to explain this so that they can be compared. So, you have to have a standard about measurement, so that in a setup or say in a company, when you report these figures, everybody will know what you mean, and then you follow the same practice again and again, so that different entities measured at different times can be compared. So, lines of code, when you report, you have to also explain how comments, blank lines, declarations, and many statements on one printable lines are accounted. So, you have another measure called ELOC or ELOC or NLOC, which mainly counts non-commented effective lines of code. So, you can say NLOC is 20, it means 20 are the non-commented effective lines of code, or CLOC, which gives you number of commented lines in the program. So, how many commented lines are available in the program, so which is a CLOC. So, these are various length related measures. Functionality, there is an important measure available in software engineering called function points, which is FP, or which is computed in terms of number of external inputs, number of external outputs, number of external inquiries, number of external files, and number of internal files. You can say represent, you can change files, interfaces, and so on. So, but these different factors are taken into account, and each counted entity has a weight associated: simple, average, and complex. Say for example, you have various external inputs, and some of them might be simple, some of them average, and some of them complex. So, this kind of measurement could be subjective. So, one person may say that something is complex, another person might put it as average. So, there is some kind of subjectivity associated here, but you give these weights, and then as per a table these weights are picked. Weights are these numbers, various numbers, and then with the formula you compute your FP or your function points measure. So, this is one way to measure your functionality, because you are talking about inputs, outputs, files used, or different number of entities used, number of external inquiries into the software. So, you are trying to measure the functionality in some sense. Then another good measure is a simple number of use cases in OOAD. Complexity, we know that we have the big O notation, and you have various kinds of complexities. You can compare them. So, if suppose you have you may say that I have my function is a constant time algorithm. So, irrespective of your input size, it takes it has the same number of steps that have to be executed. You may have a logarithmic, linear, quadratic, exponentially complex algorithm. So, once you measure this, you know how complex your algorithm is, and how the timings are going to vary based on the input sizes. So, you basically measure time and space complexity both. So, you want to also assess the space required, so that you can use your resources effectively. Now, you would like to measure structure. So, we just talked about measuring size, various aspects of size for software, that is it could be your length in terms of functionality, in terms of complexity. You could also want to measure the structure of your code or your software. So, one interesting measure is Maccabe's cyclomatic complexity. It basically measures number of regions in the flow graph, number of predicate nodes in the flow graph plus 1 or E minus n plus 2. So, in this figure you have these orange ones are your predicate nodes or decision nodes, where you have the fork. So, here you have 1, 2, 3 and 4 regions. So, or this also represents the number of independent parts that you will have to that you can use in your testing phase and so on. So, we have seen this similar pictures in the lectures on testing. So, this is one good measure that talks about McCabe's cyclomatic complexity. But you can see that a program can be very large and still have same McCabe cyclomatic complexity as that of a small program. So, it's possible. So, in a sense it doesn't it measures basically the say for example it's useful in testing, but it may not really tell you whether the program is really complex, or you may have a very big program, but it does tell you something about your decision nodes or predicate nodes or the structure of your program. And you can use this in testing because you have these number of independent paths, and you have the coverage criteria derived from McCabe's complexity. Now, we will see how coupling and cohesion could be measured. So, there are different kinds of coupling as we see on the slide. We have data coupling, stamp coupling, control coupling and so on. So, you have these through these kinds of couplings, various kinds of couplings, modules are interrelated or interconnected with each other. So, you would like to measure these number of interconnections of different kinds of coupling, or the maximum of the number of interconnections per module. Say for example, at most what is the heaviest coupling in the entire system, or average number of interconnections per module in the system. So, you can measure coupling through these coupling connections, number of coupling connections, and you can also look at cohesion. So, there is one ordinal scale for cohesion. So, you have the functional, sequential, communicational, coincidental, and so different kinds of cohesions, and you can say functionally cohesive is the best cohesion. So, which has a good, so we are putting all the components together. So, that is a best cohesion, and coincidental cohesion is that they are just together, but it is not really cohesion. So, we have put some of the classes. So, there are various classes in which you can define the cohesion, and then you can say one is better than the other. So, the best is the cohesion where which is due to abstraction. So, you are putting components together because they are achieving some related functionality, and the abstraction of the module is 1. So, that is the best cohesion possible. So, there is one such scale available, but you can also measure cohesion in terms of your code. For example, you can try to find out whether a class can be partitioned into 2 by partitioning the classes functions into 2 partitions, such that each set of functions use different set of variables. If that is possible, then the class is not cohesive if it is partitionable in that way. Or you can find out whether a class is highly cohesive or not so cohesive. So, there is a measure available in object oriented software metric suite for measuring lack of cohesion. So, we are going to have now a slide on various object oriented metrics. So, the object oriented community has come up with quite a few metrics which can measure your object oriented design and object oriented software or object oriented code. So, CK that is Chidambar and Cameron and mood metric suite are the 2 important suites which can be looked at, but there are many other metrics available. So, for example, you can measure number of methods in a class, average number of methods per class, or depth of inheritance tree, how deep is your inheritance tree. So, if it is too deep, then it is considered to be complex in terms of say the behavior, different polymorphisms possible, or the behavior or the tracing required to understand which method is going to be invoked through the inheritance tree. So, number of children, coupling between objects, response for a class or RFC, lack of cohesion among methods, that is LCOM, attribute hiding factor, method inheritance factor, attribute inheritance factor, polymorphism factor and coupling factor. So, various metrics are available in the object oriented domain as well, and the main references for these are the CK and the Mood papers. You can pick them up. Now they are also covered in many textbooks. So, some of these are quite simple, so they can be also obtainable through tools or by also manual counting. So, these measures are useful. So, as we can see that we are trying to measure various attributes of which connect to quality of the software, and then we want to feed back into the quality of the software based on the measures. For example, if you find that a class is is not cohesive, you may want to redesign your system, or if you find that there is very heavy coupling between two classes, you may want to reconsider a design, and you may want to move, or you may want to apply some refactorings on your design and readjust your collaborating classes or the hierarchy, so that these figures improve. So, if you have some quantification of your design and code, you can use that in order to redesign the system or refactor the system. So, this is a very interesting approach to also software evolution and refactoring. You can do it based on metrics as well. If you have the set of tools available, and if you have the expertise available that can make it possible to interpret these measures. So, interpretation of measures is also a very important area. So, given a set of measures, how to interpret about the quality of the software or the corrective steps that are required in order to improve on the quality. So, it is an important area, also area of research, and many interesting metrics are available, and one can go through them, and the key is to apply the right set of metrics in the right context, and also interpret these metrics so that you can feed back into the quality of software. Now, after having looked at measurement and some of the metrics and their importance in software engineering, we will now move on to some guidelines for coding in development. So, to quality related guidelines, so that if you practice these, they will lead to improvement in quality of your software. So, we might have seen these in our earlier lectures, but I am putting it down again to emphasize some of these aspects, which can be practiced even in the small, when you program in your data structures assignments, or in your any class assignments, when you code in groups, or when you code against the course projects, you can try to use some of these techniques, and they come in a long way, so that it affects the quality of your software, and they are scalable, they can be used in the large as well. So, for example, use assertions in your code from time to time. So, this is called defensive programming style. You can apply it for modules, functions, procedures, classes, and so different kinds of modules. So, why defensive? Because these can act as defense against errors which you can make. So, if you use assertions in your code, the assertions can capture various errors. So, assertions can be of different kinds. They could be preconditions, they could be used as post conditions, invariants. If you are using assertions very heavily, so if there could be practices that recommend very heavy use of assertions. So, it depends on the context in which you are working, the project in which you are working. If in a project assertions are used very heavily, they could be removed once the code is well tested, or some of them could be removed once the code is well tested. And for online defense, typically the technique used is that of exceptions. So, the software should be able to catch an error or an exceptional condition and handle it. So, that gives you a handle to gracefully terminate your software, or to gracefully handle conditions. So, we can use assertions when you are developing your code, and then possibly remove them when the code is well tested and when you want to deploy it. But you can use exceptions for online defense. So, for example, if you know that your software is not handling certain situations, and if they arise, you can create exceptions, throw them, catch them. So, this is very important, that if you know that you cannot handle a situation, you have to terminate the software gracefully, or there has to be a path to handle these kinds of failures. So, it should not be an abrupt termination. That means the software does not know that there is a fault, and then these are very severe failures. They can cause very severe failures. So, exceptions are very important, and which can be used, which should be used. So, programming languages do provide support for handling exceptions, for example, or assertions. So, you have the C assert macro, Java assert expressions, exception throw catch mechanism, the classes for the exceptions, and the throw catch mechanism of the exception handling. For example, you have it in Java and so on. So, you can use assertions and exceptions in your code frequently. So, try to use them in your smaller assignments, so that you can improve on your developmental practices. So, we will look at what are these, say preconditions. What can you do with preconditions? You can check your input parameters. For example, whether a number provided is within a range. You can check local acceptability for the message or function, whether the function add item message can be served, or is there capacity in the buffer so that item can be added. So, you can check these at the input itself as soon as the function is invoked. So, these are preconditions, and then you can write your actual business logic. So, the business logic does not have to worry about these preconditions, they will be guaranteed when you come to business logic. So, you can separate this part in the precondition code, and in post conditions you can check the outgoing results, whether value being returned is within range that is guaranteed, and you can check for the local state, that is for example, after executing your business logic, just before returning your call, whether your local state is in a consistent is consistent. For example, stack location becomes available after a pop, successful pop. So, you can check these in your post conditions. And then you have invariants, different kinds of invariants. You can have class invariants. Throughout the lifetime of the instance, the invariant remains true. For example, balance is never negative in an account, and if it goes negative, obviously there is some problem, and if that is the case, you can raise an exception or you can raise an alarm. So, the programming language has to support these, so that you can specify them, and monitors can be inserted in the code. So, loop invariants can be specified, which are valid during the lifetime of a loop. So, loop index, for example, should be within a range defined by your min max of your loop index. Now, we will talk about organizing your modules. How do you organize your modules? How do you decompose them nicely, so that you follow the separation of concerns, and that reflects into quality of your module organization. So, write related functions in one file, write a header file for this module, user program that uses this module is in a different file, the user program includes the header file, user module and function module can be separately compiled to object code, and then you can link these two together to produce an executable. So, this is a good style. If you follow this, the same thing is used in large scale development. When you actually separate the concerns, you have many modules, and you have the module signatures or the header files which specify the interfaces. So, you are separating the interfaces from implementation. So, a module that is using another module can be still developed if you have the interface for the other module available with you. So, this is what basically we are trying to capture, and this figure captures this process. So, you have this function, you have the header file or the interface defined in this file, and you have the user file. That means, you have one module here which actually is going to need this module, but you do not need to wait for this module to be developed. You can see that this path is different and this path is completely different. So, you can take these two independent paths, you can have two programmers taking these paths simultaneously, so that you can speed up the development process. So, but that the module which depends on this module has to include this function prototype, and this module uses this function prototype. So, this conforms to this prototype. So, this has to be done before you can start developing this module or this module. So, that means you can take these independent paths, you can exploit these independent paths So, once you develop this function code, you can compile it to object code, make it ready. Once you develop user code, you can compile it to object code, make it ready, and then you can link. When both are available, you have your deployed software or your e.out, for example, in your simple Unix environment. So, then you've make it a practice to use Makefile. So, you can use make utility to organize your program compilation and building processes. So, if you use sophisticated tools, these can be specified in the if you use the integrated development environments, the make files or the build files can be specified through the environment itself, so that it organizes the build on its own. You do not need to key them in one by one. So, however, for your small assignments, do try to write your make files. So, dependencies can be captured. For example, the dependencies here, that in order to produce a.out, you need this and you need this, and if you have already compiled this, if the user class changes or if the user file changes, you do not need to recompile this. So, these dependencies you want to capture somewhere, and when you simply execute the make file, when you want to build the software, you are building only those units which need to be built because the changes have been done to the files which are being used by the module that you are building. So, I have an example make file. For example, you can say these when you want to make something, when you want to make software. So, this is so whole represents the entire software. So, this is your symbol which you are using, and these are your actual units. For example, you have the inprog or p handler. So, these are some executable files you want to generate. So, when you want to build the whole software, you need to build these. Now, in order to build in program, you need to build these .os, and how can they be built? They can be built by running this command g++ whatever. So, this is your sample make file, and you can do the man page of make file and find out the format, or on the internet you can download examples, or send me a mail if you want to have these samples. Then how do you organize your code? So, do you use comments, follow conventions for names of variables, constants, classes, functions. For example, class names could start with capitals, variable names need not start with capitals, then constants can be written with all capitals and so on. So, interfaces can start with an I, capital I, and then the interface name. So, once you follow these conventions, stick to them so that you follow them uniformly, and it is easier to your code becomes easier to understand, and it can be also understood by someone else. Once the conventions are known, it is easy to follow the code. Then use proper indentation. The printout should look good. So, this is important. So, there are many good guidelines for different languages, or you can look at some of these and try to follow good indentation for your code, so that the code should look good. So, if when you take a printout, it should look good, so that it is easy to follow the code. Then when you try to develop your test cases first. So, what you want to test? So, when the software is going to be handed over to the customer, how will the customer test? So, imagine yourselves in the role of the customer and try to list the tests that you are going to plan, or that the tests that you are going to carry out on the software. So, write test cases first. That gives you a very good view of what you are going to, what is required, or what you are going to do with the software. At any point of time, let your code be executable. So, when you start writing your programming assignment, you can say, you can just start one empty main if it is a C file, and the executable file is ready, but it does not do anything. So, but however, you can now add functionalities one by one, and then it develops one by one. So, you are not writing the entire code in one big bang, and then once you compile it, you might get hundreds of errors. So, in order to avoid that situation, if you incrementally develop it, and if you keep it executable or runnable from time to time. It may run, but it may run partially. So, that is not a problem, but getting plenty of errors in one big bang makes it difficult for you to go through the errors and fix those bugs. Some of them could be syntactic, some of them could be logical as well. So, the architecture blows up step by step, or at any time the software is runnable, but with varying functionality coverage. So, this is the practice which you can put in when you do small scale programming, and it comes a long way. Also it helps you in your large scale software development. Some other good practices are listed here. You use tools which whatever is available. For example, Makefile is available, use, or integrated development environments are available, use them. So, there are various kinds of tools, and many case tools are available. So, whatever is available to you at in a given setup start. So, I am basically talking about your labs which you carry out. I say for example, software engineering lab, try to use tools, whichever tools are available. Debuggers you should try to use for debugging your code. Then produce good documentation for your code. So, documentation should not be taken as documentation for documentation's sake. It is for the purpose of understanding, firstly understanding your own code, and then somebody else should be able to understand it, modify it, evolve it. So, good documentation is important. It say when you analyze your software, when you are say if you are following OOAD, you are going to produce class diagrams, interaction diagrams, and so on. So, that gives you very good documentation, so that you can develop it well, you can test it well, you can understand your own code, somebody else can understand, evolve it, maintain it, debug it, and so on. So, documentation is very important. Pair programming is one effective practice, where if the code is very complex, you can do it in pairs. Sometimes two brains put together is a good practice. If something that you are not able to handle or not able to see, another person can see it quickly. So, usually it is an effective practice to carry out projects quicker. Then if you have hard bugs, take a printout, show it to your friend, or you can relax for some time and come back to the bug. Sometimes a bug can bug you for huge amounts of time. For example, for days a bug can bug you when you are writing your assignments. You may not be able to find the bug easily, because you are so much accustomed to your code that you do not even see a bug which could also be trivial. So, one good way to fix a bug is, if you are not able to fix the bug in say half an hour, 1 hour, you can take a printout of that portion of the code and try to read the printout. Maybe you will spot the bug, or if you are still not able to spot the bug, you can show the code to your friend and so on. So, you can apply some of these techniques. So, these are some good practices which are known to good software practitioners. So, you follow some of them, meet your local experts in coding or development, or local software engineers, so that you can put into practice some of these good guidelines which are available to you. So, this is about the factors that can go into quality software development in the long run. So, we looked at measurements and different aspects of measurement, and we also looked at some good practices which you can apply, so that your software quality improves.